So we're going to jump ahead and do chemical equilibrium, chapter 15, before we go on to chapter 12, right? Is that the next chapter? Anyway, chemical equilibrium. So a lot of things in nature are in equilibrium. So we need to understand what this concept is. One way to think of equilibrium is to remember that it's dynamic. Okay, it's not something that's stagnant. Dynamic equilibrium involves two opposing processes that are occurring at the same time. And so one analogy for this is a busy freeway. And on this freeway, you have cars going this way, and you have cars coming in the opposite direction. And so you have these opposing directions, or you could think of it maybe even opposing forces, but you have things going in one way and things going in the other way, and yet overall you have the same number of cars on each side of the end of the freeway or whatever. And the example here is given between this little reaction. Dinitrogen tetroxide will decompose into nitrogen dioxide. But two nitrogen dioxides can combine to form dinitrogen tetroxide. And this is an equilibrium, and we signify that by having this double-headed arrow, or, arrows, they're like half arrows pointing in each direction. Not sure what the exact name of those is.
Are they sideways electrons?
No, they're not sideways electrons. They are arrows. Yeah. Okay. I won't repeat that, but that's fine. And so up here we have an illustration of what's going on. We've got these guys coming apart and they're going back and forth and back and forth. And yet, you have essentially the same number. Another way to think of it is a busy airport. Middle of the day, busy airport. You've got people arriving. They're arriving on airplanes. And you've got people departing on airplanes. And yet the total number of people in the airport is probably roughly the same. But it's not the same people, okay? It's not like there was this lockdown and everybody's stuck in the airport, which, sadly could happen. But it's different people, and so it's dynamic in that things are changing, and yet the balance is staying the same. Okay, so that's what we mean by a dynamic equilibrium. And then your book has an interesting section about... I skipped the slides for section 15.1, but it's really interesting talking about definition of life. And I just couldn't deal with the slides, so I'll just tell you a little bit about it. But you should read it. Have you ever thought, well, what is life, and what's the difference between something that's living and something that's not living? You ever thought about that? So you could say, well, living things move. Well, viruses are alive. But is the moon moving?
Oh, yeah.
Yeah, so non-living objects move also. Is water moving in a river? Yeah. Is water alive? No. So movement can't be it. And so one way to define life as being in controlled disequilibrium with the surroundings. So an inanimate object like this stapler's been sitting in this room for, at least half an hour. I've never seen this one in here before. It says, biology, do not remove. Someone removed it, yeah. Because we've been lacking a stapler. But the stapler is the same temperature as the desk and the air. It is at equilibrium with its surroundings. Are you individually at the same temperature as the seat you're sitting in? No. If you were, you'd be dead, because it's like 70 degrees in here, and yet your body temperature is 98.6 degrees Fahrenheit. How do you maintain that? If we heated this stapler up to body temperature, maybe by sticking it under your shirt or something and warming it up, and then we set it back on the table, it would then be in disequilibrium with the surroundings. But if we left it there, it would come into equilibrium. It would have the same temperature as the surroundings. So one way to define life is that it's controlled disequilibrium. There are mechanisms in your body that keep your body not in equilibrium with its surroundings. They keep your temperature at a certain level. They keep a variety of differences. You could say, well, you know, your cup of Rockstar is in disequilibrium. Well, it is, you know, there's ice in it and it's colder than the surroundings. But if we left it here for a day, it would come to the same temperature.
But then couldn't somebody say the same thing about cold-blooded reptiles? Is that whole purpose is the same concept?
Well, yes, cold-blooded reptiles do come into the same temperature, but they maintain disequilibrium in other ways. So temperature is one example. Pardon me?
Oh, fire. It's not the same as the environment.
No.
It consumes, bleeds, moves.
Well, it does consume, and yet, that's a good question. I don't, my tired brain doesn't have a good response for that. I skimmed the section last night and I didn't read it thoroughly, so. And fire does seem more lifelike than many other processes, and yet it's not alive. And you could say, well, it will only do that until it runs out of fuel, and yet living creatures require fuel too, right? So these are the, you know, interesting sorts of discussions to have, and the more we understand about science, nature, the more we can discuss things like that. So anyway, that's an interesting little blurb about equilibrium, which really doesn't have that much to do with chemistry. So we'll just go right on to section 15.2, the rate of a chemical reaction.